So I'm going to solve these problems in one take so you can see how I think through things, but also so you can see how long it takes me to do these problems. Although I'll go a little slower because I'll stop to do things like this, explain what I'm doing. So this problem, there's nothing curved. This is probably an XYZ problem, so that's how I'm going to solve it. So the first thing we're going to do is draw a free body diagram. And the rule for drawing a free body diagram is to make a closed loop. So there, I'm going to make a free body diagram of A. There's my closed loop. And then you draw only what's in the loop. Okay, so here's in the loop. There's that block and this link. And then you draw the forces of everything in the loop only. So I've got the weight of A. Then you draw everything you've cut through. So the circle cuts through that link, and so I'm just going to draw there the force of the link. And I've cut through between the block and the ground. And so there's the normal at A and the friction at A. And it says that it's moving, so that must be mu A normal A. And we're using the kinetic mu. Okay, I also want to draw a free body diagram of B, so I'm going to do the same thing. Here's my loop of B. I'm going to close it, and then I'm going to draw that free body diagram. Again, only what's in B, in that green circle. So there we go. There's only the weight of B here. The weight of A is not in that green loop. I've cut through the normal. And again, this is sliding down, so the friction is opposing it. And since it's sliding, the friction force is mu times the normal. We've also cut through the link there. And so we have to draw in that link force. And let me just draw in, sketch in the link. There's the link. And since we drew the link in tension on A, that force of link equal and opposite, it has to be tension here, pulling. Okay, so what we do in statics, you would set that equal to 0. But in dynamics, you would have to set that equal to MA. And so that means that this would be MA times acceleration going down. And since the two blocks are connected by the link, it's MB times the same acceleration going down at 30 degrees. Okay, so between these two drawings, we should be able to solve for everything. Let's see if we can do that. And the ultimate goal is to get the force in the link. So let's proceed. And so I'm going to pick X and Y just for convenience. I'm going to pick X and Y to go down the plane. Certainly you don't have to do it that way, but this is what I'm going to do. I'm going to call that X and Y. And so I'm actually tilting my tablet so that I can look at it that way. Okay, so from block A, in the X direction, so take all the X components, okay, of this picture, these two pictures. So I'm going to do this one first, okay. I take all the X components of those. So I've got, I'm going to take that way positive. So sum fx equals max that way as positive. Okay. Let's do that. So we got f of the link going downhill minus the friction mu A N A going uphill, and there is, I'm going to draw an angle in there, that's 30 degrees, and so you have W A sine 30 degrees going downhill. Okay, so that's everything going in the x direction that I can see on the left hand side. And so on the right hand side, it's just MA times A. Okay, so now if we look in the y direction, going that way positive, up from the ground positive, we're going to have minus WA cos 30 degrees going down towards the ground, plus the normal at A coming up. That's all the y components on the left side equals, there is no y component in the acceleration side of the equation, so it's 0. We repeat the process for block B. So I'm going to do sum fx equals max, downhill is positive. And so looking at that, we get minus of the length, because the length is now going uphill, plus, let's see, that's 30 degrees. So plus WB sine 30 degrees minus mu B and B equals mass of B times A. And in the y direction, again taking up away from the ground is positive. What we have is minus WB cos 30 degrees plus NB equals 0, because again there is no normal component to the acceleration. Okay, so I'm going to start plugging in numbers. We have 4 equations. We should be able to solve for, I'm assuming there's 4 unknowns. We'll see after we plug in what we know. Okay. Okay, so it turns out that the mass of A is 10 kilograms and the coefficient of friction for A is 0.1. So 10 kilograms and 0.1. So equation star becomes the force of the length minus 0.1 NA plus 10 kilograms times G sine 30 degrees equals 10 kilograms times A. That was equation 1. Equation 2 is minus 10 kilograms times G is the weight, cosine 30 degrees plus NA equals 0. That's equation 2. I'm going to go ahead and put equation 2 into equation 1. And so NA equals 10G cos 30 degrees. And so we get force of the link minus 0.1 times 10G cos 30 degrees plus 10G sine 30 degrees equals 10A. Okay, and I'll call that a new equation 1. Okay, so do the same thing for B, where the mass of B is 6 and the coefficient of friction is 0.3. So 6 and 0.3. So we get from equation 3 minus the force of the link plus the weight of B, which is 6 kilograms times G, sine 30 degrees minus mu, which was 0.3 for block B, NB equals 6A. That was from equation 3. Equation 4, we get minus 6G cos 30 degrees plus NB equals 0. And again, I'm going to put equation 4 into equation 3. And so we get the NB is 6G cosine 30. So we get minus FL plus 6G sine 30 degrees minus 0.3 times 6G cos 30 degrees equals 6A. That's equation 2. So there are two unknowns in these equations, A and the force of the length, if you look at equations 1 and 2, and we're asked to find the force and the length. So we'll just solve those two equations for the force of the length, and we'll go from there. So I'm going to just, I don't know what I'm going to do. I'm going to simplify the equations first to make the algebra a little easy. So I've got FL minus, I'm going to do 0.1 times 10 cosine 30 degrees. So that's just cosine of 30, 0.866G. Okay, plus 10G sine 30, that's 5G equals 10A. I'm going to simplify equation 2. 6G sine 30 degrees, that turns out to be 3G, because sine 30 is a half. And then minus 0.3 times 6 times cosine 30. So 0.3 times 6 times cosine of 30. So 30 cosine. That comes out to 1.56. And that will equal 6A. And that's equation 2. So let me just double check that the 0.3 times 6 times 30 cosine. Yes, 1.56. Okay, so again, I'm going to rearrange these a little bit more. So we got FL minus 10A equals minus 4.134G. Got minus FL minus 6A equals minus 1.44G. Okay, and we need to solve that for F link. I wish it was solved for A. It would have been easier to do. So I'm too lazy to put it into a calculator. And then I'm going to multiply the top equation by 0.6, minus 0.6, and then add them together. So equation 1 multiplied by 0.6 minus 0.6 is minus 0.6 FL plus 6A equals 4.134 2.48. Okay, add those together. Minus 1.6 force in the length equals 1.04G. And the force in the length is minus 0.65 g, meaning the negative sign mean I guessed the direction wrong. And this problem is in kilograms and meters per second squared. So minus 0.65 times 9.81 equals 6.38 newtons. So the force in the link is not in tension, it's in compression. So there we go. So drawing that in, let me draw it in. It's going that way. 6.38 newtons, and it's going this way. And I guess thinking about it, that makes sense because A is heavier than B, and A has less friction than B, so A is pushing down on B. So that makes sense. I just thought of two more things. What would happen in this problem if A and B were switched, where A was downhill from B? And the second thing is, what would happen if A and B had the same mass and the same coefficient of friction? Think about that. I just checked this, and this is correct. And if you were to go ahead and get the acceleration turns out to be 3.42 meters per second squared, although that wasn't asked for.